is going to be, again, very exciting session today. Jochen is a professor at Berlin University of Applied Science, Berlin, from last year. Is that last year?
Last year started, yeah.
Yeah, Jochen used to work for PTV for more than 8 years as a principal product manager for micro simulation mobility. And he says, I just check off your LinkedIn, you have more than 4,000 followers.
Yeah.
Particularly, he's interested in VSIM. He's got 4,000 people keep asking him some questions, including my students, a lot of guys in Korea as well. So these days, we do have a lot of research and development projects in Korea for the autonomous vehicle, and many universities are using VSIM to do some of the projects in a very different ways.
Yeah.
So many students here, including me and faculty members, are very interested in your talk today. And it looks like a PTV user group meeting rather than the academic seminar, but it's going to be really, really fun. Okay, please enjoy and give us a hand.
Thank you. Thank you very much. So my talk will be two-folded. First, I'll talk a little bit about how to simulate autonomous vehicles in VSIM, in microsimulation, and then going a little bit a step further, if you want to do a co-simulation, which has also been done in autonomous vehicles simulation, that you couple a traffic simulator to a vehicle simulator, a specific vehicle simulator. But first, let me introduce you, and that does not work previously. Yeah, I am ESFJ. I'm very thankful. I'm very thankful about being here in Korea, and this is what I learned last night. Never heard about this personal test. I did it late night, and I probably don't fully agree. I learned the E, and there's the opposite E. And all the other tests I did, I always was more introverted than extrovert. Anyway, yeah, I'm really glad about the opportunity to come here to learn from you like that. And as Ini was introducing me, yeah, main focus was last 8 years developing microsimulation product VSIM, which I now also use at the university to teach them. And I'm a professor at the University of Applied Science. University of Applied Science is different. In Germany, we have these different systems of normal universities and University of Applied Science. Applied Science, we have 243 of them in Germany. Almost 40% of the students in Germany go to University of Applied Science. And it's a very practice-oriented university. So the goal is to make them ready for the industry as fast as possible, so that they don't have to. So yeah, we do that, and actually 1 semester towards the end is mandatory to do in the industry. So they have to go to a company and work there for 6 months. That's part of the program. This is supervision then from my side and from the others. 2 weeks back I was at the construction site because I'm in civil engineering, and I got someone from the construction. I have no idea about what they're doing, but that was very interesting. And we supervise them in there. They often get paid. And actually I learned about probably 80% of our students, even in the second and the third semester, they have a job already at the company. So they almost all work already while studying, even though it's a full-time study. So for us, of professors, does it also mean we need to have at least 3 years of experience, industry experience? Otherwise, you cannot become a professor at the University of Applied Science. When we develop our lectures, when we develop our new programs, there's always someone from the industry in the advisory board to develop that. And I ask a lot from the industry, what do students need to be fit, to be ready for what you're searching for, and that keeps updating our lectures to keep up to date with the industry's needs. And that is well received from the industry. They use the students quickly. So that is University of Applied Science. I'm not sure if something like that exists here. but in Germany we have these two different. We do less research. So for example, in my case, I don't have any PhD students. Currently, I could have, but I think average PhD student per professor is something like 0.456, so it's very low. Not a lot of professors have actually a PhD student, so less research. Okay, now come to autonomous vehicles. The future might look very bright. We can have very effective traffic control. That's one scenario how a future could look like. Maybe looks not so safe, but it is actually safe. There is no accident in that scenario involved. But the question is, how will that look like, and how will the efficiency of autonomous vehicles be like? And that's part of my talk today. So the company is developing these algorithms. They promote themselves as, yeah, we're building a safer driver, and actually I think 94% of all accidents are based on human errors. So that's a big potential. If that is being automated, probably won't become zero, but of course less accidents as now. But there are many questions. There are many challenges. And now, why is it important? I heard in one conference, I was in the US, they were thinking about building a new highway. And they needed to make a decision if that's a 3-lane highway or 4-lane highway. The demand, which they estimated for the next 3 decades, 30 years, said in, I don't know, I remember exactly, in 17 years, we would need a 4th lane to maintain like the growth in demand. And the decision was then, okay, would we not have in 15 years a technology that we have higher efficiencies on our road, so that we maybe can save the third, that's millions of dollars, hundreds of millions of dollars, that we save the 4th lane, because in 15 years we don't need that much capacity anymore, because we have a more efficient way on how vehicles drive. For example, if we have a connected autonomous vehicles lane and they drive in very short distances, having a high throughput. And then we don't need the 4th lane anymore. And that is actually decisions we need in ideal way already today. I'll show you one study, and maybe this lecture is also a little bit European perspective. Lisbon study. What they did is they took a city, the capital city of Portugal, and they tried what would happen if we replace all demand, every single origin destination trip in the city on a day, if we replace that with an autonomous mode. What would happen then? So all bus trips, everything being replaced. The only thing we keep is high capacity public transport, because if we would drop that, then our cities would be destroyed, or the big cities. We need high capacity. Bus trips, single person trips, everything is replaced by taxis, and we would only need 17% of vehicles. That's a big opportunity. It's not a good future for Germany and for Korea, because we don't sell that much cars anymore. Yeah, only that. And of course, the other big opportunity, we don't need parking anymore. We can give this percentage of parking spaces to others, restaurants, whatever. Yesterday we heard the city should become, should more have the function of hospitals and other things. So that's an opportunity then, but there's also a downside. And the downside is, in that scenario, there's 44% more kilometer driven. So we only have 17% of vehicles, but these vehicles, they operate not only 5% of the day, they operate almost all day long, and need to travel more. Pick up here and there, and going back, picking up people. So, and that's of course not good if we have that much more kilometers traveled in our city. So there are opportunities, but there are also thoughts about it. Who knows that picture? No one. What is it? A little bit of a strange rhinoceros, is it in English, right? Yeah, rhino. That is from a kind of, in our culture, famous painter, Albrecht Dürer from Germany, painted 1514, I guess, so very early. And the interesting part is Albrecht Dürer, the painter, never have seen a rhinoceros himself. There was no Google where you can check up how it looks like, this animal, 1500 something. Someone just told him it looks like that, it looks like that, and he, according to what he heard, was trying to build that. And you see here this armor, which he knows from knights and everything, probably. That's what they told. But it looks very good. Yeah? And what we try to do now with autonomous vehicles is very similar. We try to paint a picture of something we don't know. Yeah? We don't know how autonomous vehicles will drive if we have 20%, 50%, 100% market penetration rate of them. So we try to predict the future, try to draw a picture and hope that it's going close to what we will observe. This morning in the car we had a conversation. I heard from researchers in the 70s, they, for example, predict that in 30 years' time, meaning in the year 2000, they thought that they will be able to forecast the weather 1 year in advance. So if you plan your wedding, then in 8 months you can select a date where it's sunshine. Yeah? That's what they thought, yeah? But they were wrong. Yeah? So there are, of course, predictions which are positive and negative, but it's important to draw the picture as best as possible. So how will the future look like? So if we just think of here, we have capacity of our roads. Yeah, currently around 2,000 vehicles per hour per lane, passenger cars, what we have as a capacity. And now we have more, I use the term CAV for connected autonomous vehicles. Yeah? So if we have higher share of connected autonomous vehicles, how will that change? One thing I see a lot of researchers being having the same opinion is that we have a high share, ideally 100%, we have a higher capacity compared to today. Because like just technically they can drive in shorter distances to each other. That's proven, that's possible. But what happens in the transition phase? Goes it directly up? Stays it almost the same for a while? Or even goes it down because they drive very carefully in the beginning? So that's an important question, because before I show you some study, I would like to make a small poll with you. So if you can just scan that on your smartphone, and then you should be able to enter a number. And please enter a number in percent. For example, -10 if you believe, if we have a market penetration rate of 10%, if you believe the capacity will drop. So then -5, -10. If you believe the capacity with 10% market penetration rate of autonomous vehicles will increase, then type a positive number in percent. Just don't use the percent symbol, just use the number. Okay? Did it work for some? Does it work? Yeah. Okay. So just 12 more seconds, and then we look at the result. 3, 2, 1. Okay, I stop it now. So 23 people have been used. So the average is 19%. So you think when we have 10% of market penetration rate, 9%. The distribution, some of you say it will decrease the capacity. Most of you people are optimistic. Some even say 50% going up with 10% market penetration rate. That would mean connected autonomous also influence the human behavior. Otherwise, I think we cannot achieve that. Interesting, interesting. One more question. What will happen at 50% market penetration rate? You use the same code, and it should ask you now for enter another number with 50%. You can use the same link. You just need to refresh the page. Then you should see the other answer, the other question. So we keep that short, only 10 more seconds.
So
50. Should say on the question. Yeah. Okay, 3, 2, 1. I stop it. So now we are at 44. So 50% capacity increase with 50% of autonomous vehicles. Okay, you're very optimistic, what I think. Yeah, but it's a we don't know. So we'll find out. So thank you for joining. I'm always trying to get more information. Now, just a very simple model would be, okay, nowadays we have a vehicle, capacity 2,000 vehicles per hour per one lane, if the headway is 1.8 seconds. That's what we have today. And if we just assume, okay, we have now a headway of 0.9, then we would double the capacity, if we would have 100% of autonomous vehicles. If we would have 50% of the autonomous vehicles, then we would have 3,000. This is what you also estimated with 50%, with such a simple model, of course, with a lot of assumptions. Literature is also optimistic. That was from 2012 already, so it's quite an old study. The interesting about that is there were interviews made with males and females, and you see the difference. Males tend to be more aggressive, so they could make the settings in their vehicles, which gaps they were driving. And ACC could be considered as human-driven, and CACC, that's connected adaptive cruise control. So if it's connected, that could be considered as like that it will be in the future. And they were much more comfortable with this connected automated cruise control. And going down to time gaps, that's not the full headway because it doesn't take the vehicles into account. So headway is from front bumper to the next front bumper, so taking the vehicle. Gap is only from the rear end to the next front end. So that's a difference here to be made. But here it's also closer and going up from 2,000 almost to 4,000. So that's one study made very early. A very German prominent study, so kind of from a government institution being made, they were not so optimistic here. They were saying, okay, it goes down because they assumed for an autonomous a time gap higher because an autonomous vehicle needs to drive according to the law. In Germany at least, but I think in Korea it's the same thing. If you look at peak hour, the gaps are not as they would be allowed, by law. They go on dark amber, so even if it's turning red, the last one will go in extreme situation, because this is always what we're interested in. What is it in the peak hours? We're not interested in the Sunday morning. What is capacity on Sunday morning? We need the maximum throughput at peak hours. And in peak hours, we see that. We see these small gaps by human drivers, and autonomous vehicles, they just can't do that. If they are connected, then we can go down. And then we see the benefit. So they prognose like, okay, here's a market. Here's the change in capacity, 30%. This is one. That is the years here. And this is the market penetration rate. So the penetration rate of human drivers goes down, even to 2070 to 0%. And then we have here different levels of these vehicles, and then in the end benefit from it. So there was a prominent study saying it goes down in the beginning. Another it's a completely different approach from a study was made here from someone who was saying, okay, if we have autonomous vehicles, they drive as it would be a railway, and they need to behave on these technical standards now in California for high-speed rail. And that regulation says the maximum longitudinal acceleration is very low, 0.5. The deceleration is also very low for high-speed rail trains. The question is, of course, can you compare vehicular traffic with high-speed rail on the streets? Yeah, but with that, just with that assumption, if probably it's not right to take this assumption, but if we do that, then capacity would be reduced by minus 21%. If the signal time is adapted, because we have very slow braking here, so we need to give longer yellow, then it's even worse. Another approach, another result. So we see a lot of results. One of the, what I think, most prominent result in how the future of in traffic flow capacity will look like with connected autonomous vehicles is in the highway capacity manual, the newest release. You know, do you follow that? Do you read that? Highway capacity, okay. So you've seen that already, these, okay. Then I don't tell you, some of you. So what they did is, they used also simulation, and they looked, okay, with different penetration, market penetration rates, 0%, 20%, 30%, they plotted here speed flow charts, and saying here for different starting capacities, they have this different starting capacity thing, and then reaching different capacities here. And you see here, it's getting better, it's getting better. In here on the x-axis, you have the flow, passenger cars per hour per lane. And summarizing that in these charts, capacity will also increase with 2 lanes, with 3 lanes, with different starting or base capacity here, up to 3,200. So it's not going 100% capacity increase, but well, from here almost, from a low starting capacity, not. Of course, the result here is independent of the starting capacity, because in the end we have 100% connected autonomous vehicles and they drive similarly.
Connected and automated at the same time.
Connected and automated at the same time. Yeah.
They
Yeah.
share the information.
They share the information. Yeah. Otherwise, it's not possible. I'll show a graph later on that as well. So these are the numbers, and the numbers here is the percentage increase, meaning, for example, if we have a base capacity of 1,800, then for 80% of proportion of connected autonomous vehicles in traffic stream, we'll have a 60% increase, meaning capacity is multiplied by 1.6. Yeah? And they publish these in these very, very official guidelines. Yeah? And with that, you can work, and that is probably the most solid. Yeah? Simulations have been done with Vissim here as well, which I sometimes thought, oh, I know how many bugs in Vissim exists, and they derive these capacity levels from it. But yeah, probably there's no other way in doing that. So they did that also. I'll go through a little bit faster now here. This is for movement. I'm busy. Is that for? Yeah, that is for signalized intersections. They did also for signalized intersection these factors here, and that is here they don't have the factor. They just have the base saturation flow. But you see also here this increase, and they have it also for roundabouts. For roundabouts, this is with 0% market penetration rate, and you can read the capacity here on the y-axis. And here is the conflicting flow rate. Of course, the more cars you have in the circle, the less capacity you have at the entry of the circle. And you see here how the capacity goes up at 100% market penetration rate. So they have it for almost all facilities. They have these capacity adjustment factors, how they call them. Okay, so we have them. But what do we do? And you said that there's a lot of studies being made here in Korea. How can we do our own studies? And you do that already. So during the time I was at PTV, we did was, okay, we'll make this driving behavior available to all customers who want to do that. Because not everyone has the driving behavior of an autonomous vehicles. Ideally, and we hope to get information here from Groupe Renault, which is an OEM, but we also had Vedicom, who was developing also a French company, an algorithm for autonomous vehicles, and we want to look how they drive and replicate that in Vissim to make it available for everyone. Because not everyone has access to data, not everyone has access to the algorithms and how they drive. And even if you have to, you still have to program, you still have to make that connection. Yeah, and cities were interested. It's like we have 4 cities, European cities from different countries. And yeah, we made the studies, and we looked now here. A little bit sad was that Renault, they were saying they changed their strategic in autonomous vehicles, and that's why they dropped out of the project, so we didn't get any data from them. But we got these prototypes of autonomous vehicles, and we drove them, and we looked in how they behave. So for example, here there was a manual driver in the front, and then there were 2 vehicles which were automated driving. Sometimes the connectivity was switched on, sometimes was off. And what we see here is the vehicle speed. So if we have higher speed, then on the y-axis is the distance between the 2 vehicles. And of course, there's a linear increase. So with a higher speed, we have a higher distance, which is kept between this prototype. That's the first thing we were, and now it comes to the connectivity part. Here we see here the delta velocity. So this means the leading vehicle was faster. No, the following, this vehicle was faster than this one. So they're going like that. And negative is the leader is faster than the other one. And here's the distance. So what you see here is if connectivity is switched on and they drive the same speed, delta velocity is 0, then here at speeds of 120 kilometers per hour, they keep a distance to each other at 14 meters. If connectivity is switched off, they need to go back to 38 meters distance. So there's a huge difference between if they are connected and if they're not connected. Also, what we saw is they could not really, even in connected, they could not really keep the exact same speed. So there is a little oscillation, and here there's a stronger oscillation. So around the delta velocity 0. Of course, the following vehicle tries to keep the same speed as the leading vehicle, but it's not perfectly possible. So we then thought, okay, we need to develop a new algorithm in VISIM, automated vehicles, but it was estimated to be a huge development effort, and that's why we tried first to calibrate the existing model. So this is what we observed from the automated vehicles, and this is VISIM default behavior, human behavior, and there's a big difference. So we tried that, and in the end we achieved something like that. You see, this is not perfect like that, but it is getting close. We achieved that. We needed to do some adjustments to the model. We needed to do some extra parameter to the model, but we came somehow close so that we felt confident in providing it to our customers. We also developed a platooning algorithm, which basically makes perfect car following driving behavior. So that can also be done. That is really connected. So then they get the information from the leading vehicle. With all the others, it isn't. Yeah. And that were then these new driving behaviors. So this is normal human behavior. And then we had 3 different, and that's just depending mainly on the time gaps. A cautious driving behavior, normal driving behavior, and aggressive driving behavior. You see here the time gaps between them. Red cautious having more headway compared to the human driving behavior. AV normal smaller, AV aggressive even smaller. But you see, it's not always the same. There is some variation. They just drive aggressive, but it's not like connected. Here with the platooning, this is very stable. Here, that is really perfect connected vehicles. What we also introduced is, for example, if you have different manufacturers, so the yellow ones, they can talk to each other, the purple ones, they can talk to each other, but purple and yellow cannot talk to each other. So to model that, that is also possible that you can make decisions about, okay, what is my leading vehicle? And depending on my vehicle, if it's also a yellow vehicle, then I can be connected, keeping shorting distance. If that's a purple vehicle and I'm a yellow vehicle, I cannot talk to them, and then I need to keep larger headways. So that was also implemented. Resulting that in speed flow diagram, here you see clearly the aggressive with the smallest headways, of course, reaching the highest maximum throughput, the highest flow, here in the speed flow chart. Good. Looking now at the cities, not all cities did micro-simulation experiments. In that project, we also expanded VSUM, the macroscopic tool from PDV, so that it's capable of handling autonomous vehicles and estimating more on the demand, the routing side. But the Helmond, Milton Keynes, and Gothenburg from Sweden, they did some micro-simulation experience, and I'll show you some use cases. So Gothenburg, they have an extreme growing population, and they want to know long-term, a lot of construction are needed to prepare the infrastructure for that population growth. So they wanted to do that, but that was macro. And they wanted to introduce a shared space. Shared space meaning vehicles don't have priority, and basically everyone on the road, if it's pedestrian, cyclists, or motorized traffic, they all have the same rights. And looking at such simulation, autonomous vehicles, Helmond in the Netherlands, that was very classical traffic engineering, signalized intersection with pedestrians. The Netherlands, they have a very, very high mode share of cyclists and pedestrians, and how the transition will be from interurban highway to an arterial, city arterial. Milton Keynes looking, it's a city with crazy number of roundabouts, like every time you need to go a roundabout. They wanted to have this priority junction operation at roundabouts and also waiting and drop off. They have lots of parking spaces around their city, and they want to investigate, okay, if we would have pick up and drop off, so basically you're driven through your workplace, you get out from the main door, and then your automated vehicles will find a parking spot themselves. And city was just doing macroscopic analysis, Stuttgart. So one thing I wanted to share from that, what the cities did, is an interesting experiment design. And the approach was like that. So we had here different stages. So that's basically the future. Today here, we have no autonomous vehicles. Then we have an introductory phase established and revealed. So further in the future, the more we go down. But then we had here, for that different futures, we had defined different AV penetration. So we were not looking at simulations with 100%, but 25, 50, and 75. And the difference between 1 and 2 for the different futures was, okay, at the beginning, the assumption was in the beginning, the autonomous vehicles, they behave very cautious, very careful. Then they drive more intermediate mode, and in the end, they drive more advanced. So you see here, for example, for introductory 1, we still have 25% penetration rate, but out of that 25%, 80% in 1 are basic AVs, 20% intermediate, and for the introductory 2, we have switched it. They are more intermediate autonomous vehicles than basic. Okay, and that field, okay, that makes sense to use that. But there's another thing which comes into account, and that is road types. So the assumption in the project was also for different road types. For example, in the city, we'll see autonomous vehicles driving much, much later compared to highways. Highways is easy, but in cities, driving is difficult, it's hard. So there was this differentiation made for basic AVs. We use for motorway and arterial cautious, but for urban street and shared space, even there we still use manual for the basic AV. For the intermediate AV, we use for motorway and arterial normal, and here cautious and shared space, we never used the all-knowing AV behavior. That's only be used for motorway and arterial here. So, and the cautious, normal, all-knowing, that is basically what you could imagine. This is a time gap. Cautious, very cautious, yeah, that's what it says. Normal is like a human driver, and the all-knowing, we later renamed it to aggressive. That is really short, I think 0.6 in time gap. So that combines, again, that's the same graph as the previous slide. You see here, so if we have introductory phase 2 and we are looking at urban streets, we have 20% manual because we use this. We use basic AV, and basic AV for urban street is manual, so 80% manual. And for urban street intermediate, we use 20%, we use cautious, and that's the cautious. So that's a methodology behind to predict. So not only 5%, 10%, 30%, there's also this dimension in what is the progress in autonomous vehicles behavior, because they learn they will be getting advanced in the future, and also this dimension of different road types. It's easy to drive, it's hard to drive. And that combined led to these different scenarios. And that was what they were executing. And that is results from Helmond from the Netherlands. So these are basically now the times, base, intro 1, intro 2, established and prevealed. This is urban, and we see here travel time. Travel time going up for human-driven vehicles and for autonomous vehicles. That is because, we jump back to the last slide, we have here intro 1, intro 2. Intro 1, intro 2 uses cautious driving behavior. Cautious driving behavior is longer time gaps than before. And that's why higher time gaps come into play, come into the simulation, and then it increases the travel time. And only then later on, we have the normal driving, and the aggressive is not even used here, then we benefit. And in the end, we don't benefit. In the end, it will be something like today. If we have that, not this all-knowing aggressive driving behavior. Yeah. Higher AV, higher travel times for AVs compared to human-driven vehicles. Why is that? Does anyone an explanation? What do you guess? Why is a travel time for an AV higher than for a human-driven vehicle? How fast do you go if there's speed limit shown of 50? Who's driving exactly 50 or under 50? Yeah, you're honest. Who's driving faster than 50? No one? I don't trust you. I don't trust you. Normally, at least in Europe, Korean you might be very correct, but in Europe we all go over speed a little bit because we know the car, what is displaying. It's 55 displaying, but if you check GPS, it's actually just going a little bit faster. So we use that and go a little bit faster. And that's also, of course, the case for simulation. The desired speed in Vissim language is higher for human-driven vehicles. And of course, AVs, we assumed they don't go over speed. These I learned today also in his car. If it's automated, he cannot go over speed limit, right? Yeah, you cannot, yeah, which makes sense. But, and that's the other side, then the delay is less. But that's, of course, it's just because of how Vissim calculates the delay. It's the desired speed. So humans want to go at 60 kilometers per hour, but they had to stop at the signal. And then they accumulate more delay compared to if you would have wanted to drive 50 kilometers per hour. Okay. One other section is now, why do we do Vissim simulation at all? So the benefit of simulation is clearly we verify what we have thought of. We use it for communication, a lot of videos being produced to show it to the public. We detect unaware issues. We compare different scenarios as we did. We give a decision support, and we evaluate the impact of certain assumptions, like autonomous vehicles. And the main part is this one, detect unaware issues. And that is very crucial and a strong argument for simulation. And I want to dig into that a little bit. There's a quote from the former Minister of Defense in the US, Donald Rumsfeld, that there are no knowns, the things that we know that we know. You know that you know that you, how high you are or what you're doing. But there are also things that we know that we don't know. I know that I don't know what to say, hello, I'm Jochen in Korean language. I know that I don't know that. Yeah? I know things which I don't know. But then, and that's the problem, there are things we don't know that we don't know it. Yeah? And this is where we make mistakes. Yeah? You're not aware something, and this is why you do the studies. You learn things that you know, but probably before you entered your master's or your bachelor's, you didn't even know that such things exist, yeah? Especially in transport modeling. And this is what we want to identify. So there are these aware, things we are aware and things we are not aware, and things we know and things we don't know. And of course, this is the most important thing. We are aware and we know it, and that's the risk. We know something, we don't know something, and we are not aware of it. But there's an extra dimension on top of it, and how do we deal with that? Do we make it right or do we make it wrong? So in the end, we have these different dimensions, and of course, this is the ideal case of planning. Things we know and we are aware and we do it right. If you know it and you are aware of it and you do it wrong, that's criminal. You know, I don't make a mistake. And that happens as well. If you are aware, but you don't know it, and you do it right, it's just gambling. You know you don't know it, but I'll just do it. It's either you have luck or you have bad luck. If something you know but you're not aware of it, that's something we call routine. You just do it. You don't really think about it, but you do it right. If you make it wrong, this is just careless. You just make mistakes. Actually, you should have known it, but you just didn't thought about it. You didn't aware it, and you make a mistake. Same with unknowing. So you're unaware, and you don't know it that you're unaware. So these are the things you don't know that you don't know it. If you make it right, it's just random that you make it correct. It's luck, and it's bad luck. So, and with how, in the end, we want to be here. We want to do it right, and we want to be aware, and we want to learn from it. So, and of course, everything doing it wrong, we want to try to avoid. And what you can do is, so this is the right thing. These are the black swan events, how Donald Rumsfeld, or in that quote, calls it. Things we are not aware and we do it wrong. This is what simulation now helps very much to achieve. So we create awareness. We look at the simulation, we try to interpret the simulation, and then we see in the result, I haven't thought about that here. I know it, but I haven't thought about that. And here are things, a simulation, why is that result? I need to dig deeper. Why does that happen? And then thinking about talking to someone and making aware what is going on. So this is what we do. From things we don't know to things we know, we analyze. So we create knowledge. So think about, we ask someone, why does it happen? Creating knowledge. And then in the end, do it wrong, do it right. We do that normally through external check. We give someone to model, to audit your model, to check it, and then pass the check, and then we are here. So in that process, simulation helps a lot to avoid these black swan events, things you're really not aware, even you know it or you don't know it, and this is a strong argument for simulation. So that's one argument, but simulation is not always the answer. So in the upcoming, so that's from the draft of the what's called Traffic Simulation System Manual. So something which the US considers as the HCM for simulation, which was planned to release like even 3 years ago. So it's always delayed, but it will come out in the future. And there it says most cost-effective approach to meet the required output. So always think of what do you want to get? What is the required output? And then choose the most cost-effective approach to meet it. And microsimulation is not often the cost-effective approach to it. It's most expensive, most complex, but of course it has the highest accuracy and the most detailed performance measures. And things, if you're not aware about it or how that works, simulation helps you to think about it, to make that transparent, and to avoid the mistakes. but often simpler approaches like deterministic models, like the HCM, or I think I heard you have a Korean adaptation of the HCM. Using that is often enough to do a traffic analysis. So also these fake poems, I have seen so many things making wrong using microsimulation. Things you can easily, if you wanna get a study from me about anything and want to get this and that results, I can make it for you work. No problem. Yeah, there are so many parameters you can adjust, and you can, like this misuse, easily. Yeah, you can fake everything, and that is of course a big thought, misuse. So listen to your lecturers, what they tell you about simulation, so to make it right. Yeah. Okay, now on autonomous vehicles, it's not only about throughput on single lanes, there is much more. And I refer here to also European project, InfraMix it's called. They looked at many more scenarios, also using microsimulation. And in that project, they even coupled it with a vehicle simulator. And they looked in like active traffic management. What can we achieve with dynamic lane assignment to automated driving? What can we do with roadwork zones? How will traffic flow improve in bottlenecks, and so on and so on. So there are much more, of course, opportunities which we have in traffic management perspective with autonomous vehicles. First, with the information, we have the data. We know where vehicles are. We know where vehicles want to go in an ideal case. And there's much more possible here. And this is what they did. So also on intersection, think of RAM metering systems. So there we can achieve it. And even a system optimum, not a user optimum, system optimum, you could achieve that. So some vehicles drive longer, but in the end, the total delay time of all will be reduced. And that's what you would have as what you would like to want as an economic. But I'm not going too much into detail. I'll just show you some tips and tricks and for if you want to do modeling autonomous driving in VISM. So there are these coexist parameters which you can adapt, of course. So from coexist, from the observation we had with these prototypes, we set the time gaps to 0.6, 0.9, and I think 1.8 for and there's more parameters you find here in the driving behavior. There's even a tab, autonomous driving, which you can set also for the platooning, and you can make your assumption. Additionally, there is this lane-based driving behavior. Lane-based driving behavior means you have a different driving behavior if you drive on a different lane on a link. So why is that? You change your lane, and suddenly the vehicle will change the behavior. Where do you have that? Huh?
There's overtaking lane on the highway.
Overtaking lane on a highway, there you typically accelerate. You go faster. You may accept also shorter time gaps to the leading vehicle. That's right. Thinking of, like here I have an example. It could be that in the future, as I said from the US case at the beginning, we could have something CAV lane, where only connected autonomous vehicles are allowed to drive, because they have an efficiency advantage. They can go with very small headways, and we wanna sort basically. We wanna sort the ones who can drive in shorter distance compared to the human-driven vehicles, and then achieving a higher throughput, something like that. Or even in merge areas, you sometimes use higher safety distances so that other vehicles can more enter the highway easily. So therefore we developed that time, back then when I was at PTV, that specifically for automated driving use cases. There is some examples also for communication, how to model that. You see them. One is that one is an example where a vehicle is broke down on the highway, and then to inform the other vehicles and to reduce the speed. Adopting speed to arrive at green. The vehicle will get the information when the next signal, the upcoming signal, will be green again, and adapt its speed so that it doesn't need to stop but goes directly through. Or in terms of routing, there you can make decisions, okay, the autonomous vehicles, they get routing advice and they know where to go, and you can do that. And this concept is what we introduced in Vissim back then with especially user-defined attributes and with attribute modification. I think it's very powerful. Previously, we had to write scripts like that, and that can be replaced just by these 4 elements. And these elements, these are attribute modification, and whenever you need to do something in Vissim, like for autonomous driving, but not only to autonomous driving, where it goes beyond the capability of Vissim, I recommend you first try that with user-defined attributes and attribute modification. That's so much easier. I did that the first time now with my students, and when they said, oh, now they don't need to do that anymore, they use that, and oh, they were all happy with that. So just as one example, here for this arriving at green. So imagine you have a signal, the signal is red, and the vehicle gets the information, okay, in 20 seconds, the next signal will be green. And then your vehicle will adapt the speed so that it arrives at. So we have the target attribute for each vehicle, the desired speed. So we change the desired speed. Desired speed is what speed do I want to drive. And we do that, we filter first only for the vehicles who are able to receive the signal information, only then, and then some conditions, if the speed is higher and smaller than that, if you can make it basically in the green time, then change the speed, and then we calculate the speed. If it's smaller than the original speed, blah, blah, blah. So I think you get the idea. It's for me not to learn how that is being done, but just the methodology of this attribute modification, and that is quite powerful to use. So that's some tips and tricks. Create your own attributes as much as you want, and use this attribute modification. That helps you very much in model some scenario. Even that model runs completely without a script. I think it's also available in the examples. That is basically a delivery. We have here 4 different depots, and they are creating stochastically some demand from the depots to deliver packages from one terminal, it's called terminal, to the other terminal, and we have these 4 taxis or vans who deliver the parcel, and they are sent then to specific location to pick them up and to drop them down. Okay, in terms of automated vehicles, there is even more, which I didn't talk about it. So what we normally consider in transportation is we make a location, the decision to go to a location, we take a vehicle or we buy a ticket, depending if we go public transport or vehicular traffic. We have activity choice, destination choice, mode choice, departure choice, route choice, speed choice, lane choice, and in the end, in the operation, headway choice. So many choices. So which parts affect autonomous vehicles? That is something AVs will decide. And we can then estimate what is the maximum throughput. Yeah? Here, route choice, will that influence by AVs? Maybe. Maybe we'll have platoon lanes where you can go faster, and you may change your routing just to make advantage of that. Maybe. Here, mode choice, destination choice. Well, if you have an automated vehicle, you don't have a driver license required. Just hold in the car. In Germany, it's about 4,000 euros. So it's a little more than $4,000 to pay a driver license. So not everyone gets one in Germany. Yeah? And if you have the opportunity suddenly now, okay, I take a car, which previously was not, of course that will change then with AVs. Destination choice. Travel time doesn't matter so much. If you can sleep, continue sleeping in your car while commuting to your workplace, you're willing to drive longer, because the cost for you of driving is not that hard. So that will change as that. Acquisition of vehicle, sharing is easier. Yeah, you can rent my car, no problem. I don't need to drive it. It can automatically drive. So it's much, much more as what we consider in microsimulation. And that is, of course, very interesting for the future and to paint this Reno, how it looks like in total. We just look now more of throughput. That will be interesting. Change of location, rural areas easily to access is of course also an option. Like I would think, but our models, if the travel time doesn't matter so much, and you can easily drive somewhere, maybe we see people going more out of the city, if of course the capacity of the road capacity is enough, because the commuting time is not considered as so bad as it is now. Because I don't need to drive, but I don't know. So AVs will influence our behavior. In the end, I'll just end with a quote. The best way to predict the future is to create it. So you are transportation engineers, the decision makers of the future. And instead of just looking how it will become, of course we have opportunities to decide and to create this future through regulation, to what is allowed, what not. So we don't need to wait for that, but we can influence that, and you can influence that. So, and that is of course important.